So we've established two kinds of calculus. And those two kinds of calculus, well, here are the two problems that gave birth to them. On the left-hand side, we have the tangent line problem. And what was it that solved the tangent line problem? That was differential calculus. So remember that the problem was, I need to find the slope of the tangent line given only one point. Oh, that's pretty tough to do. Hey, all you got to do is take the derivative, and you got it. Okay, and then we have the area problem, which was about trying to find the area underneath the curve for some weird reason. And what solved that was integral calculus, right? So it was all about breaking it up into rectangles and making the width of each of those rectangles as close to zero as possible. That's a limit of a Riemann sum, which became a definite integral. And at first, people thought there was no relationship between those two things. I mean, because look at it. Slope of a tangent line, area underneath the curve, what's the connection? Here, take a look at it like this. Okay, so for the tangent line problem, we start with a secant line as an approximation for the tangent line. And to find the slope of a secant line, you divide delta y by delta x, right? And when you take the limit, of course, that turns into dy dx, which is our derivative, okay? So you're dividing there. Now then, for the area problem, we broke it up into rectangles. Break it up into rectangles as an approximation here. The rectangle that surrounds our function here, we have a delta x for our width, and we have a delta y for our height. Isn't that what we did? We had a height, we multiplied some sort of width, and to find the area of each of those rectangles, you would multiply those things, a delta y times a delta x. And then basically you take the limit as that delta x approaches zero, and you're going to get the exact area underneath the curve. Now, does it seem obvious that these things are inverses of each other? You've got division over here with slope, and you've got multiplication over here with area. And that is exactly what's happening here and the reason why differential calculus and integral calculus here are inverses of each other, okay? So here is the fundamental theorem of calculus, the second fundamental theorem of calculus. This one is the one that allows us to find the value of a definite integral involving an antiderivative. If f is continuous on the closed interval from a to b, stop right there. There's the first condition to use FTC, is that your function has to be continuous on some sort of closed interval. And f is an antiderivative of f. So look over here, underneath here, we have this capital F. We know that that's supposed to be some sort of antiderivative of your integrand here. Then the definite integral from a to b of f of x with respect to x is equal to f of b, that's the upper limit, plugged into the antiderivative, minus f of a, that's the lower limit, plugged into the antiderivative. And this is usually how we write it. We find the antiderivative of whatever our function is, and then over on the right-hand side, some people just put a straight bar, like a such that bar, or just one kind of right-hand bracket with the upper and the lower limits on it. And that just is a reminder that we need to plug in the b first, minus plug in the a, okay? If our function is non-negative, then the area underneath the curve is essentially equal to the difference of our limits of integration plugged into the antiderivative, right? That's what we found back on that parabola question where I was trying to put all of these dots together for you. All right, so here's how you apply the fundamental theorem of calculus step by step. So the first one is just find the antiderivative. And it can be any antiderivative. You do not have to worry about the plus c, okay? And then you're going to plug in your limits of integration, your b and your a, and then you subtract those two values. Always the top one minus the bottom one, right? And then you'll see in just a second, you don't have to worry about this constant of integration. I'll show you that in just a second. And since this is a theorem, mathematics, you know, is based on proof. There will be a proof of this as a separate video. But before we look at that, let's come over here and let me show you. C doesn't even matter. All right, so let's say, for example, I have the definite integral from a to b of little f of x dx, okay? And then whenever I find its antiderivative, I'm just going to call this f, capital F of x, and then let's say that I remembered our constant of integration, r plus c, okay? And then I needed to evaluate that from a to b, Okay, so I need to plug in the b first into the antiderivative. This should be equal to f of b plus c minus, here let's put brackets around this, f of a plus c. And now whenever I remove the brackets by distributing the negative sign, what happens to the c's? You get f of b plus c minus f of a minus c after you distribute, and then obviously we can see that the c's just cancel, right? And then that leads us to f of b minus f of a. All right, let me make another connection for you, and that's going back to, it was one that we couldn't do by hand. It was the one we just looked at a series of pictures for. It was this f of x, which is equal to the definite integral from 0 to x of the cosine of t dt. All right, now, I know now, based on this fundamental theorem of calculus, how to evaluate this definite integral. It doesn't matter that the upper limit here is equal to x. I'm just going to treat it in the same exact way that I did this, okay? So I need to first find the antiderivative of cosine of t. Antiderivative of cosine is sine, so sine of t. And then I'm going to evaluate that from 0 to x. So now I just plug in my x and my 0, and I'm going to subtract them. First comes x, so sine of x minus sine of 0. What's the sine of 0? It's just 0. So we get sine of x. And that's exactly what we saw from the graph, that this is equal to the sine of x. All right, now what happens whenever you find the derivative of this function? So down here, find the derivative of this function. F prime of x is equal to the derivative of sine, which is cosine x. And that's the first fundamental theorem of calculus. When I take the derivative of this function that's based on a definite integral, they cancel each other out, they are inverse operations, and I just get the original input back, which is this cosine with just a change of variable here, cosine x.